this computer. Go.
Okay, cool. Hello, yeah, my name is Malte. I will be talking about window functions today. I first heard about window functions almost a year ago now, and I didn't really take them serious. And then I stumbled across them recently again. And then I learned more about them in preparation for this seminar, because Lev asked me to present about them. And now I'm actually quite amazed by how, versatile and efficient and also simple they are. So I'm quite excited for this presentation. The purpose is to introduce you guys to them. There's only 11, 12 functions you really have to know, and I will cover or try to cover most of them today. And then maybe we can have another session in like a couple of weeks where I walk through more advanced topics of how you can actually solve like real business problems with them. But for today, I only plan to cover basic functionality for them. Most of the information comes from this book here. The guy who wrote it, he's pretty amazing. His name is Ben Itzigan, and he is a genius when it comes to SQL, and especially Power BI is pretty cool as well. So yeah, I highly recommend that book. I'm halfway through it now, and I've learned quite a bit. So I can include that in the presentation, the ISBN. That's something you guys want. But yeah, so in terms of window functions, they were introduced to the SQL standard in 2005. And then over the years, there have been some updates to it. I'm not going to dive too deep into that. But I will tell you that for this presentation, I will mostly talk about window functions in T-SQL, like the beginning slide said. Depending on the system you're on or on the server you're running, there are different functionalities and different functions work on different systems. But I will mostly cover T-SQL here. Sometimes I will try to give you workarounds for functions that I think are useful, but not implemented with T-SQL. Hopefully there will be soon, but yeah, in those cases, I will simply try to give you a workaround. But yeah, let's stop the talking and actually dive into some problems. So the first slide here, basically the goal is to give you a little bit of a motivation to actually listen today and not just browse around on Google while I'm talking. So this is a pretty common coding problem. It's called the island problem, where you have a table with a list of values, and you are asked to identify the islands within those values. So for example, given that input, you would expect that output. So for example, the first island would start at value 2 and end at value 3. And then the second island would start at value 11, end at value 13. 27 is the third island, and then fourth island, and fifth island. So pretty simple. Now the question is, how do you actually implement that in SQL? And what I will do is I will actually, let me move the code down a bit. I've written up most of the code, so we don't have to watch me typing, but I'll first create the table with those values. And then I'll first try to do it in normal SQL. And then after I've done that, I'll compare this solution to the solution with the window function. And hopefully the window function solution will be more elegant, but we'll see, I guess. So talking about solving this without window function, one way to get there is you first find a group identifier. And what I mean by group identifier is for each island, you label it by a group. So for example, value 2 and value 3 would be labeled A. 11, 12, 13 would be labeled B, and then 27 would be C, and so on and so on. And the way you can accomplish it, it's a bit challenging in normal SQL. It's two nested subqueries, so we can see one subquery is here, and then it goes all the way down, and then there's another nested subquery there. So essentially what you're doing is the way you want to solve it. Is you want to look at each value in this column, and you want to check if there is a value greater or equal to the current value, which next value doesn't exist. So for example, for value 2, there exists a value that's equal or bigger to it, value 3, that doesn't have a next value. So it satisfies the condition of an ending island, and that's what you see here. So you first check if it's bigger than it, and if it's bigger than it and doesn't exist, and the next value of it doesn't exist, then it's an ending or it's a grouping qualifier. But you'll see if I run this, you get this output. So you can see that each row has one identifier here. So pretty cool, fair enough. And now you can group, as you might have seen it up here, you can group this query by this grouping identifier, and for each group, grab the minimum and maximum value, and you have your desired output, which is this. So fair enough, that's what I've done here. I basically nested our original query into CTE, and then wrap this into another query. And if I run this, fair enough, you see that I get those starting and ending values. So pretty neat. But if you would have looked at this query without any context, it probably would have taken you a couple of minutes to figure out, what's going on here. And then at the same time, it's horribly slow. I mean, those are only 9 rows, but if you are looking at the same problem with, I don't know, 100,000 rows, it's just not feasible because of this nested subquery nature. The data is being scanned almost twice entirely for each row you're looking at. So it's super slow, and hopefully with the window function, we can get around there. I won't really explain you what this window function does because it's so simple. If I simply run it, you'll see what it does. It's called the row number window function. So for each row, it just finds the row number. So if I run this query, I'll talk more about syntax in a second. It generates one row number. So what makes the window function is basically this over clause. You can see here in this case, there's something within the over clause, but usually, or for most window functions, you can run it without the over clause. In this case, there's something in it because we want to order by column 1. Now for this specific problem, you might ask, okay, hey, what's the point? Like, how does that help? We have the same number literally right next to the original column. It might become more apparent if you actually take the difference between column 1 and the row number. See what the output of this looks like. And this actually looks quite similar to the grouping output we got earlier. So you can see that for each island, the difference between row number and column actually is constant. And once we jump to a new island, we get a new difference. So you can actually use this row number as your column identifier. And what I've done here, I've basically, like above, I've wrapped that query into the CTE, and again, grouped by the row number, or in this case, the group, I named group. And if I run that query, I'll get the exact same output. And it's much nicer in terms of syntax and looking at it. And it's also faster. It scales linearly, and it doesn't give you any performance issues. So it's super cool. That's just the introduction for my presentation. I hope you guys found that helpful. And in terms of to understand why window functions can be helpful. And now I want to dive into the 4 main types of them before I give you examples for each of them. Yeah, so there are 4 different types. I will spend probably a fair share of the next 25 minutes or so talking about the aggregates, because they are not only the easiest to explain, they also help you to understand the window function elements the best. But yeah, they're pretty normal in terms of syntax. There are a couple ranking functions, and some are more useful than others. I'll talk about them. There are some statistical functions that basically help you to rank them in terms of normal ranks and percentile ranks. And there are also offset functions. They help you to grab different rows from different frames or windows, but I'll get to that when we'll get to that. So let's talk about elements of window functions first. And I'll promise I'll only spend a couple of minutes here because it's easier to learn that in practice. There are 3 main elements, and they're all defined within the over clause I just mentioned. Depending on the function you're using, you can mix and match them. Usually you can use all 3 of them. For a couple of them, you can't use all 3 of them. But again, I'll get to that later. Partitioning is basically like grouping. So you can, for example, in this syntax here, you partition by country. This is the same as, not the same, but in terms of syntax, it's the same as grouping by country. The only difference to the group by clause is that the partition by clause leaves all the rows intact. It doesn't collapse them into an aggregate row. So it's pretty neat if you want to maintain that information. The ordering clause, it's pretty helpful for, like the name suggests, ordering the rows, but that sounds redundant, but it isn't, because if you want to ensure that your output of your query is the same every time, It's pretty useful to include that as a tiebreaker. Sometimes, SQL under the hood has some kind of performance engine, and the performance engine might decide, okay, hey, for this one query execution, I want to return all the rows in that order, but for the next one, for some reason, it's a different order. So if you want to ensure that your output is the same every time, I recommend including this. I usually try to include it whenever I can, because it just gives some clarity to the output. And then lastly, the framing part, from my understanding, well, it was for me, it was the hardest to understand, but once you get it, it kind of makes click. Framing is like the having clause in the normal logical ordering. It helps you to restrict the window after you partitioned it a little bit further. The syntax, I'll get to that in a second, but essentially after the order clause, you include which rows you want to include in the frame. And there's for example, here say rows between unbounded preceding and current row, which basically means nothing else in plain English than all the rows before the current row. And there's another option called rows following, which will basically means the opposite, it means from current row to the row to the end. But again, I'll explain that a little bit better in a second. One thing I want to mention here pretty briefly is that you can only use window functions in the select and order by clause. And that's all theory, I promise. From now on, I'll dive into examples. And actually, let's start with them right now. First, I think let's talk about aggregates. Like I mentioned earlier, I think they're the easiest to understand. Here's just the brief syntax for aggregates. You have your function, then you have the over clause, and you have aggregates, you can see. And then within the over clause, you can define the partition, as well as the order and window and framing clause. This all probably looks like rubbish right now, but I promise it will make sense in just a bit. And yeah, I will just start by running this first query here. And by the way, I'm using this T-SQL 4 database. You can grab that online. If you just Google T-SQL v4, it will pop up and you can use it for all those queries. So yeah, so what's going on here? So let's just go step by step. That's the output of it. You can see here in this first part, we are summing the value column over. This indicates that it's a window function as sum all. Since the over clause is empty, it basically means that we don't have any partition, meaning there's no grouping, there is no ordering. So ordering is kind of random here, and there's also no framing. So this means that in theory, we are summing over the entire table, which is 830 rows, and we are returning the grand total of the value column, basically. And that's what we get. And as you can see, the output is the exact same for every row. Now, on the other hand, we have the second row here, where we partition by customer ID. And as you can see, we sum the rows for each customer. So it's pretty straightforward. You can include some ordering and framing here, but I don't want to do that yet because I want to go slowly. So here, the next query, it's pretty neat because you can include calculation directly with your window functions. So you can calculate grand totals pretty neatly. Again, same syntax as above. We sum over the entire partition. So no, over the entire window, so no partitioning, which will reveal the grand total. And if you divide each value by the grand total, you get the percentage related to the grand total. So 0.06% for the specific row. And then if we partition by custom ID, you get, and let me grab a screenshot, I'll actually do that later. You'll get the percentage per customer. So in this case, there's 6 orders for customer 1. And if you add up those 6 orders for customer 1, you'll end up at exactly 100%, which makes total sense. So that's kind of as a broad introduction how the partitioning works. And now I want to talk a little bit about the framing and the ordering. So this next query here, as you can see, again, it sums quantity from a different table over the employee ID. So it groups employees and sums the quantity column. It orders them by order month, and it grabs all the rows between unbounded preceding and the current row. So that might sound very confusing, but I will run this and I will grab the output and we'll head over to Paint and I'll try to explain. Oh, sorry, it was the wrong shortcut. I will try to explain this visually. Okay, so what's happening here? So first, and first we are partitioning by employee ID. So if I go to paint, you will see that there's a partition right here. That was the wrong button. That's the first partition, employee 1. Then the second employee will get a second partition right here. Now, the next step is that we order by order month. As you can see, all the values are ordered in ascending order. So as you can see, that's the default. And next we are calculating, or we only considering for each row, the rows between unbounded preceding and current row. Unbounded preceding basically means all the rows above the current row, and current row means current row. So, sorry. The first frame will be this row, and it sums the value of quantity for all rows in that frame and returns it in running quantity. So you get 121. Then the second frame moves one run row down, will be this frame right here. Let me draw a frame right there. That will be the second frame, and then it will sum those values. The third frame for row 3 again will be this frame, and then it just moves down row by row, and you can see the pattern now. That's how it's calculating this running quantity and this running total all the way until this row right here, and then it will actually collapse this frame and start over again at the frame below. So pretty neat feature, and it allows you to pretty easily calculate those running totals. In the next example, I will talk a bit more about the different framing options. So as you can see here, I've defined different framing options. Rows 1 or rows between one preceding and one preceding. This basically grabs the previous row, but you'll see that visually as well. You get rows between one following and one following. This will grab the next row. And you get rows between one preceding and one following, which is basically one row above and one row below the current row. But again, it will be easier if I just show you guys the output of that. And let me head to paint again and show that. Okay, so you can see that we have a partition here again, same partition, and again I didn't choose the rectangle. And now for the first row, might be easier with arrows this time. I'll just point it out with the mouse. For the first row, the previous quantity is null because there is no previous quantity. The current quantity is 121, and then the next quantity basically looks down one value because for this specific, why is it not letting me draw it? Anyways, for this specific row, the next quantity is 255, and then the average quantity for row 1, it's kind of interesting because the frame, as I defined it here, the frame was one row unbounded preceding, rows between one preceding, so one above and one below current row. But since there's no previous row, it just returns the average of the first and second row. And similarly for the last row, it only returns the average for the last and the previous row. So pretty straightforward. And I think these examples where you compare them, in terms of how does the framing actually work, help you understand what's going on here. But yeah, one thing I want to mention is that for here, we only looked at the rows option. In the SQL standard, there's an option called range, which is a little bit more dynamic in the sense that it allows you to ask different questions in a row. But I didn't cover it here because it's only partially implemented in T-SQL. But again, with range, you can answer questions like, hey, give me the total quantities for the period starting 2 months before the current period and until the current period. So it's a little more dynamic compared to the rows option, which can basically answer questions like, hey, give me the total quantities for the last 3 points of activity. That doesn't really sound like a difference for now, but trust me, if you look into the differences, you can see that range is a little more advanced in terms of how dynamically you can identify patterns. One thing I want to point out is that for aggregate function, you can basically interchange them and it won't break the code. So since we defined the frames, now the frames are still the same. We just perform different operations on them. So as you can see, now we summed them and it's the same output because there is no sum in the previous row. So it's 0. But the point is that you can basically copy and exchange the aggregate functions in here and it won't break the code, which I think is pretty neat. But anyways, yeah, so that was the first section. I'm running out of time, so I'm breezing over the second one, which is going to be ranking functions. First one is the row number function. You already saw that one. It basically creates a row number for each row. It can be very useful if you use it right. I recommend to always include an order by clause, even if there's one included inside the over clause. Outside of it, because the output here, it looks like it's ordered by row number, but it isn't. It's just arbitrary returned like this by the optimization engine. So it's good practice to always include it on the outside. If you run it like this, you will be sure that this is the same output all the time. I got a little bored once, so I tried to implement the same functionality with the count function, the count window function. So you can do that pretty easily. You have the count function, and then you again order by order ID, and now you're framing it with this frame statement. Notice that I'm not including the second statement, which is rows unbounded proceeding until current row, which I did here, and current row right there, and current row. This is kind of the default, and SQL is smart enough to understand that you're trying to say, okay, hey, all the rows until the current row, so you don't have to actually include that. And if I run that, sure enough, you get the same output. Next function in the ranking part is the entile function. Entile function is fairly useful for data scientists, I would say, because you can split the data into different sections. So the syntax is right here. So entile means you split the data into 10 different parts, all of equal size. Again, in the over clause, we have the order by statement. And again, with the row number statement. So if I run this, you will see that there's a tile number here. Now, if we know that there are 830 rows within the entire table, this would mean that until row 84 or 83 would have tile number 1, and then starting from row number 4, tile number 2, and then all the way down until we get to tile number 10. So it's pretty straightforward. I can change it pretty dynamically. So if we go to 100 tile size, then we expect, so it's pretty interesting. We expect 8.3 tiles, because obviously can't do it. So now we have 30 tiles with size of 9. So it divides 830 by 100, which is 8 with a remainder of 30. And so the first 30 rows will all be size 9. And then after size 9, each row will be size 8. So that's kind of how entile deals with values that aren't divisible by the input value. The cool thing you can do with entile, or not with entile, but with the row number, is paging. So if you ever, for some reason, need a page number in your tables for whatever that might be, you can use this functionality here. You have a row number, and then if you have a page with, let's say, 10 rows per page, you grab the row number, you subtract one of it, and you divide it by the page plus 1, and that will be the page number you get. So for example, if we have a row 11, and our page size is 10 rows per page, then we expect row 11 to be on page 2, right? So if we execute that statement, fair enough, it's page 2, and this is exactly what this row number function does here. So it's pretty cool for paging, if you ever need to do that. Secondly, we have rank and dance rank functions. These functions are quite similar, but easiest to understand when I run them. You will see why they're called rank and dance rank. So we have row number. Let me make that a bit bigger. We have row number, which basically numbers the rows based on what the ordering was, the order date. Rank ranks them, like the name suggests, but it skips rows. So there are 4 dates with 4 rows with the same date of May 6th, and they all get rank 1, and then it skips rank 2, 3, 4, and goes straight to rank 5. Dense rank, on the other hand, it goes to 2, 3, 4, 5, 6, so it doesn't skip rows. It kind of compresses the output. So depending on what you need for your functionality, you can either choose dense rank or rank. But yeah, that kind of concludes it for the ranking functions already. So you see how we are breezing through them. We have 2 sections left. The first one are statistical functions. And there are 2 different kinds again. There's percent rank and cum-dist functions. And I'll talk about those ones first. And then there's 2 other ones, which I hope I have time to cover. For this exercise, we're using a different table, which is basically a table of test scores for students. And I'm trying to get this up here. And you can see, there's different students and 2 different tests. And for each test, each student has a score. So now we can use those data or this data to rank students. And I'll try to get this down again. All right. Okay, so the way percent rank and cum-dist are calculated is pretty straightforward. From my understanding, and Lev might correct me on that later, but from my understanding, the cum distribution function is similar to the cumulative distribution function in a way that it tells you, okay, hey, what is the probability that x or one specific value will take a value less than or equal to x being the probability returned by the function. But we'll see what I mean in a second. This is the math behind it. So I don't know if I want to go too deep into that. Maybe I'll explain those variables. Okay, so the rank of the row, RK, is the rank of the row using the same window as the distribution function window specification. It's a handful, but essentially it's basically the rank of the row within the window specification. I mean, like I said it, but I hope that makes sense. NR is basically the total number of rows in the window partition, excluding the framing, and NP is the number of peers. So basically all the rows that are less or equal to the current row. And based on these variables, you can calculate the percent rank and cum distribution. So if I run those, and you can see we have the function here, we have the over clause, we grouped or partitioned by test ID, and we ordered by score. So we did that for the percent rank and cum distribution here. And if I run those, we get the following output. Oh, I see we have a message in the chat. Okay. This is the output we get. So you can see that it ranks each student on how good it is compared to peers. So with a score of 50, you are the worst person. And then with a score of, I don't know, 75, it's the median, or the 50th percentile. On the other hand, the cum distribution shows you what are the odds of people having the same score less than you. So as you can see, it's pretty straightforward. And it again grouped it by test. So like I said, very basic examples, but hopefully I can talk about how you can implement them with more advanced solutions later on. I had some fun and I implemented the same functionality without those functions, but I won't talk about them now because I'm running out of time. Instead, I want to talk about the inverse distribution functions. So instead of returning a percentage, they accept the percentage as an input and return a value from the group. So in fact, they are the opposite of the two functions we just talked about. The syntax, however, is slightly different. So you use a with and group statement here, meaning that those functions are actually called ordered set functions, which are slightly different than window functions, but I'll cover it here anyways. And yeah, so percentile discrete returns the first value in the group whose cumulative distribution is greater than or equal to the input. And the percentile cont is pretty similar, slightly different in the math behind it. Again, I can't go into details here because I'm running out of time, but if I execute them, you will see the difference. As you can see, given a percentage of 0.1, what score would I have to get the percentage? And it's 50 or 54 for the cumulative or percentile continuous function. But that's just the underlying math behind it that makes it slightly different. But again, I'm sorry, I won't have the time to explain that. But yeah, those are basically the opposite of the percentile ranking functions, if that makes sense. Now, the last part are offset functions, and they are very straightforward. They help you to grab values in the frame that are related to the current row. For example, in category 1, actually they are related to the current row, lead and lag. And in category 2, they aren't related to the current row. They are related to the start and end of the frame. So looking at examples, we have lag and lead. So lag will grab the values 1 behind and lead will grab the value 1 above. Again, here I specified 2 and 9.9, but you will see what that means in a second. The previous value for the first row in the partition is null, and the next value is 330. The second to next value. Remember, I specified a lead of 2 here, so that means that instead of grabbing the next value, we grab the second next. And now you might ask, okay, why are there no nulls here? There are no nulls because the third argument in the lag and lead function allows you to get rid of nulls. So if I would do the same here, and I would say 0.00, then I would basically get rid of all the nulls in the previous value column. That's just a neat way to exclude them. Yeah, and lastly, this will be hopefully the last example I cover. First value and last value, they allow you to grab values in the frame based on the first and last value, like they explain it. So if I run those queries, we have, again, partition by customer ID, order by order date. We're looking at the following frame, all the rows above the current row, and we only care about the first value. So as you can see, this is the frame, and we're always getting the first row, and we're always getting the last row of the frame. One thing maybe to point out is that we cannot rely on the default here, which would be unbounded proceeding. If we would run this, oh, sorry, I think I got my syntax wrong slightly. Yeah, I continue, so I won't cover this. There's a trick here where you can't rely on the default for the statement, because then you only get a current row, which will result in the wrong value. But that's a slightly involved topic. But yeah, usually there's some kind of comparison involved. So you want to take a difference, between the first and last value of the order, but you can do that again directly in the query here, which will give you the difference, between the the current value and the first value and the last value. But again, it's pretty straightforward. And yeah, I think that's it for today. I don't have time to go into ordered set functions or nested subqueries, but I'll try to do that in following examples, hopefully. But yeah, hopefully you guys took something away and it wasn't too in depth. And yeah.
It was very good, Malte. Thank you.
Okay. Yeah. No worries.
Let
Very
me stop.
interesting, honestly. Yeah.
Thank you, Malte.
Yeah. Working a lot of with this